This is Chemistry, Unit 12, Gases. Here we'll look at Charles' law. Now the Charles in question is French physicist Jacques Charles, who's the man in this image. What he's actually famous for is for being the first person to fill a balloon with hydrogen gas and completing a solo hot air balloon flight, which is awesome. Now he determined that the volume of a given amount of gas, that's our V, increases with the temperature of a gas. Hence the hot air balloon ride. There's the hot air, the temperature went up, so the volume of his balloon went up, and up he went. Now pressure, P, and the amount of gas, N, remain constant, so P and N are not involved in Charles' law. Now when dealing with Charles' law, you must keep the temperature in Kelvin. So let's take a look at some data, and then I will show you what the data looks like on the NASA website. So let's just check it out first. What happens to the volume? Well, it went up and up and up. So we increased the volume. What happened to the temperature? Same deal. It went up and up and up. So what does this actually? So here it is. So check out the graph this time, right? You can see that it looks different. It's not that curve anymore. So as you increase volume, you increase temperature. Decrease volume, decrease temperature. And check out the little experiment here. Mass stays the same. Pressure stays the same. But now look at this. Temperature is increasing. So what's happening to that volume? It's going up with the temperature, or it's going down when you decrease the temperature. So what does this tell you? Is this a direct or an indirect relationship? This is a direct relationship. As the volume increases, the temperature increases. And this also works in the opposite direction. As the volume decreases, your temperature decreases. All right, so Charles used hydrogen, and every gas could be used in these types of experiments. But now what you should notice is this last column. So similar to Boyle, he not only took this data, but he started to manipulate it, right? He looked at some different mathematical relationships. So in Charles's case, he took the volume and he divided it by the temperature. And look what happened when he did that, right? So again, he used hydrogen, but you can use any gas that you'd like. Every gas will have different values for V over T, but they will remain constant under different measures of V and T. There were no pressure changes, and the amount of the gas remained the same. So mathematically, V over T equals a constant. So how do we use this? Well, the same way we used Boyle's law, right? You can take any two experiments and compare them. So if you compare the V1 T1 to V2 T2, if you divide the volumes and the temperatures, you get a constant. Therefore, Charles' law is V1 over T1 equals V2 over T2. So again, you're comparing two different situations. So it was mentioned that Charles' law needs to be solved in Kelvin. So where's this Kelvin coming from now? Well, when volume is plotted versus temperature, so here's volume, here's temperature for both graphs, volume and temperature. Straight line results, right? So here's this one is just hydrogen, but these are different gases, right? Here's hydrogen compared to other gases. Okay, when this graph is extended, so we usually end our graphs at 0 degrees Celsius, right? That's pretty common for us in science. When it's extended until the lines intersect the x-axis, the lines all meet at the same temperature, regardless of what gas it is. And that temperature is right here. So it's actually negative 273 degrees Celsius, also known as 0 degrees Kelvin. Where's this coming from, this Kelvin? Well, it's for Lord Kelvin, or Sir William Thomson, who's in this image right here. In 1848, he suggested that at this temperature, all particles have zero kinetic energy, or are no longer moving. The temperature scale was changed to the Kelvin temperature scale based on this argument. And if you want to see a little bit more information about what this actually means, can we actually achieve that kind of a temperature, you can take a look at this video for some further explanation. But for your purposes, you need to know the Kelvin scale and the fact that you have to add 273 to go from Celsius to Kelvin. Okay, but that's where the number and the name are coming from. So now let's try an example. So if a 30.0 liter balloon at room temperature, 25 degrees Celsius, is taken outside at negative 10 degrees Celsius, so that's quite cold, what happens to the volume of the balloon? Why do I have those numbers up in red? So before I do anything else when I'm dealing with Charles' Law, I don't want to figure anything out about the problem, you have to change your temperatures. That should be the first thing you do when you are solving Charles' Law. So this 25 degrees Celsius, when you add 273, now becomes 298 K, and that's what you use in the problem. Negative 10 degrees Celsius, add 273, 263 Kelvin is now what you need to use in the problem. Every time. Okay, so that being said, now look at your situation. What do you have here? What do you know about the balloon? It has 30.0 liters for its volume, and it's at room temperature, which is 298 K. Okay, you take it outside, the temperature drops, you're at 263 K. What's going to happen to that volume? Well, just according to his law, if the temperature drops, the volume should drop, but you got to prove it. So here's the setup. So it's V1 over T1 equals V2 over T2. So your initial volume of the balloon, right, is 30.0 liters. The initial temperature, 298 Kelvin. You're trying to figure out what happens to the volume when you decrease that temperature to 263 Kelvin. All right, so to solve this, we use a method called cross multiplying. So if you notice, I did not take 30 and divide it by 298. I took my 30.0 liter and I multiplied it by 263 K. And then if you look at the other side, I took my V2 and I times it by 298 K. See the cross, right? See the X? You cross multiply. Okay, now when you do this, you have a setup that looks like Boyle's Law. So now you should be able to finish it. So the first thing I'm going to do is multiply. And I did follow my significant figures. And then on the other side, nothing changes. So notice the K and the L also stay on the left. Those have not been eliminated yet. Nothing's been crossed out or canceled. But now how do you get the V2 by itself? Remember, this is being multiplied by 298. So you need to divide. And now you will see the K's cancel and you're left with liter, right? Because we're solving for volume. And now make sure when you solve this, you don't just leave what's in the calculator, which is 26.48 liter. You need to match the significant figures. Each of these has 3, so the proper answer is 26.5 liters. So does that actually make sense? Yeah, temperature dropped, so the volume dropped.